Hello guys, in this video we'll be looking at the Gauss-Siedel method. First we will see how this method works and then we will get into implementing this method in C++23. See, this video is a sequel to the previous one I made on Jacobi method. It follows the same kind of patterns and what we are doing is approximation under a tolerance range. In this method, we approximate the value and we check if we are inside this tolerance limit, and if we match the condition, that means we have found the value for this particular tolerance range and we exit out of that. Now let's see how this works. For this method to work properly, we need the input matrix to satisfy either of these two conditions. That is, it should either be strictly diagonally dominant or it should be a symmetric matrix. Now what does it mean for the matrix to be diagonally dominant? It means that for each of the diagonal elements in each row, the value of the diagonal element should be greater than the sum of the non-diagonal elements. Now this condition should satisfy for all these rows, and then we can say that the matrix is diagonally dominant. And now what does symmetric matrix means? It means that the transpose of the matrix should be equal to the original matrix. So if we represent that in equation form, we get this: A is equal to A transpose. See, here these two matrices are symmetric and this one is not symmetric because the transpose is not same as the original matrix. Now this is the equation for the Gauss-Siedel method. Assuming we have the system Ax is equal to B, where A is the initial input matrix, X is the value that we are going to find, and B is all constants. K here is the index for the iteration, like the one we use in for loop. Alright, so x of k plus 1 is the value that we are finding in this iteration, and L is the inverse. L inverse is the inverse of L matrix. L matrix is the matrix with the lower triangular values including the diagonal, and we multiply this inverse with the value of B minus U times x of k. So U is the upper triangular matrix. It is strictly upper triangular because we are not including the diagonals. Now what is this x of k? See, x of k is the previous value that we find. Now we know that the iteration starts with k of 0. When k is equal to 0, it means that x of 0 is the initial guess. And what is the initial guess? It is the value that we provide to the function. So in our case, it's basically all zeros, like a vector. So from this initial guess, we find the first value of k and we plug that back inside this value for the next iteration. So the basic idea is that we use the previous value to find the next value based on this equation. Now we need a stopping condition for this method. We have got two options. The first one is the recommended one, where we use the tolerance option. We take the newly found value, that is x of k plus 1, the old value, we take the difference and we take the magnitude of that, and we check if that scalar value is less than the tolerance. If it is less than the tolerance, we exit out of the loop. And the second one is to use max iterations, where we put the maximum iterations for the loop to a large number like 10k, or we can increase that. As we increase it, the overhead will increase proportionally with that, so it's recommended to keep it low and play with the tolerance values. Now let's get to implementing this in C++23. Here we have the implementation for the Gauss-Siedel method in C++23. So we have got two matrices A and B. So these are the input matrices. So first of all we print both of them, and now we get into the actual code. See, first we check if the A matrix is diagonally dominant or if it is symmetric. Either of these two conditions should pass for us to proceed. So if we go to this helper function, you can see it checks the diagonal elements are dominant. We add the sum and we check if the sum is greater than the diagonal element. If it is greater than that, we return false, and then we check if the matrix is symmetric. So it's also pretty intuitive. We check if the I and jth element is not equal to j and ith element. That means the mirror image is not there. If that is true, that means we can say the matrix is not symmetric. Alright, next we make the initial guess, that is x. So we set x as 0 initially, and then we put all of this stuff inside this Gauss-Siedel method, a, b, x, and this tolerance value. Now if we go into this function, we can see that we are also taking in this max iterations value. It is set to 10,000 by default. Now if you remember, we need two matrices L and U, right? So we initially set both of them to the value of A matrix, and then we need to chop off some of the values and set those to zeros. So we have this helper loop here. So I will briefly explain what this does. So for U, we do not want diagonal elements, right? So if it is a diagonal element, we set U of ij is equal to 0, and we do not want to remove the elements of L, right, in the diagonal area. So we put this condition here. We only set L to 0 when I plus j is less than or equal to j plus j. That means the lower triangular. We only set the L elements to 0 when I plus j is less than or equal to j plus j, and it should also satisfy this condition, that is I should not be equal to j. That means it should not be a diagonal element. And if it is anything else than that, we set the value of u at this indices to 0. Now we have got the L and U matrices. If we add these two together, we will get the A matrix back. Alright, so next we find the inverse of the L matrix. So this is also a helper function. Because the L matrix only has the elements up to the diagonals, we can easily use forward substitution to find the values of the inverse. So it's pretty basic. Next we go into the actual stuff, that is the iterations. We have the index going from I0 to max iterations. So remember in the presentation we were putting k as the index, right? So it's the same thing here, and we have the formula here. So x of k plus 1 is equal to L inverse times b minus ux. We divide this function into small parts, that is this stuff, and we add them together into this one. So ux is multiplying u and x together. So these are all small helper functions that I have, and then we take the negative value of ux, that means simply multiplying it with minus 1, that is multiplying with scalar that we provide, and then we take the difference of b minus ux, that is this one, and then we multiply this inverse of L and b minus ux, so that is this step. So that is the new value x of nu. Now we could stop here and go to the next iteration, right? But we have to check if the tolerance value is achieved. Now for that, remember that this x value is actually a two-dimensional vector, as you see here. We cannot do norm operations in that. We need to convert that to a single dimensional vector. So we use the std views transform that we have in C++23. I think it released in a previous version. I am not exactly sure about that. And we convert that to a vector. We take the first element of each row. Basically it's like a single dimensional column, right? Take the first column of the matrix and convert it to a vector. Simple stuff. And we do that for the new vector as well. So we get two new vectors, x vec and x new vec, and we set the x value to the new value only after getting the new vectors. Now we find the difference between these two vectors, x vector and x new vector, and we find the vector norm, and we check if the vector norm is less than the tolerance. By vector norm I mean the magnitude, because p is equal to 2, and we know that p vector norm where p is equal to 2 is simply the magnitude of the vector. So if this condition is met, we break out of this loop. This function straight goes to this return value, and if this tolerance value is not met, we just simply exit out of this loop and it will normally return the value. Now let us try running this program. Now I know the output of these functions are 1, 2, minus 1 and 1. So we have got pretty accurate values. Now we can modify this using tolerance. So if we increase the tolerance, we actually decrease the tolerance values to some smaller value, we can see we get to the result much accurately. See, we have got much better accuracy, and it's very close to the actual value. So yeah, this is the Gauss-Siedel method in C++23, and I will see you in the next one.